Santia bought a house in 2001. The value of the house increases 3% each year. If the price of the house is $350,000 in 2025, what was the value in 2001? The formulas we'll be using today are y is equal to a times b raised to power t. Y is equal to a times 1 plus r raised to power t, and y is equal to a times 1 minus r raised to power t. We'll be using these formulas to learn how to handle exponential growth and decay. Welcome guys to Valeto's Maths Academy, and today I'll be teaching you how to calculate exponential growth and decay. If you've not seen our class on indices and logarithm, I suggest you should do that first, as it is going to help you to understand what we're doing here. Okay, we get into the class. Exponential growth occurs when a quantity increases by a consistent percentage over time. The model is given by y is equal to a times b raised to power t. This is for exponential growth, but it can be modified into y is equals to a multiplied by 1 plus r raised to power t. This is for growth, exponential growth. This is because the rates might come, arrow stands for rate here, the b stands for the rate. So the rates can come in different forms. That is why we have two different equations depending on how the rate is given. And then for exponential decay, it is also modeled like this: a times 1 minus r raised to power t. This is for exponential decay. So guys, this topic is very important to every person, because in one time or another you need to calculate the growth of an asset or any item, or its depreciation or decay. Okay, we'll look at the first question. A population doubles every 5 years. If the current population is 2,500, what will it be in 20 years? Okay, so is this a growth or decay? This is a growth because it is increasing. So now to calculate what the population will be in 20 years, we'll apply the exponential growth formula, which says y is equal to a times b raised to power t, where y is the future value, a is the present value, b is the rate. We can also use r, remember, either we use b or we use r depending on what we want to get, depending on the question actually. And t is what? The time. Okay, so now if we substitute what we have in the equation into this, we're going to have we do not know the future value. That is what we have been asked to calculate. What will be the population in 20 years, and the present population now is what? 2,500, and the rates, we are given that a population doubles every 5 years. So it means that the rate is 2, it doubles 2. And the time they want us to calculate is in 20 years. But if you take a good understanding at the equation, you'll see that we're told that the population doubles every 5 years. So what it means is in 20 years, it's going to double how many times? 4 times. Because 20 divided by 4, 20 divided by 5, we're told to look for it for 20 years. And it doubles every 5 years. So it means that 20 years divided by 5 will give us 4. So it's going to double, the population is going to double itself 4 times in 20 years. So applying the formula, so the population after 20 years now will be A, which is 2,500 multiplied by B, which is 2, raised to power 4, because it's going to double itself 4 times in 20 years. Once you're able to place the values correctly, the equation is half solved. So we then have y is equal to 2 raised to power 4 should be what? 16. So we have 2,500 times 16. And y is equal to what? Y is equal to 40,000. Okay? Now, I like mathematics because you can always check yourself and know if we're correct. Since this is not too long, let's try to work it manually and see if we're correct. We are told the population increases. This is for a check. Let's check ourselves. Now, we're told the population increases 2 times every 5 years. So, and they want to know what it will be in 20 years. So what it means is that the first 5 years is going to double. So for the first 5 years, it's going to be 2,500 times 2, which is 5,000. This is for the first 5 years. For the second 5 years, it's going to be, remember double, it's now going to be 5,000 times 2, which is equals to 10,000. This is for the second 5 years. This is for the first 5 years, second 5 years. Then for the third 5 years, it's going to be 10,000 times 2, which is equals to 20,000. This is for the third 5 years. Remember, there are 5 years in 20 years. And for the fourth 5 years, it will now be 20,000 times 2, which is equals to 40,000. This is for the fourth 5 years. Okay, and that is how we arrived at 40,000 using this very simple formula. Okay, so this is for population growth. This is for exponential growth. Remember in indices, when we talked about exponential exponents, indices, index, power. Exponent means power, raising something to a number of power. Okay, we proceed. Question number 2. A bacterial culture starts with 5,000 bacteria and decreases by 10% each hour. How many will remain after 8 hours? How many bacteria are we going to have left after 8 hours? So is this an exponential growth or a decay? This certainly is a decay. From the word here, decreases, you should know. Okay. So we apply the formula for decay, which is y is equal to a into 1 minus r raised to power t. Okay. Now, a in this equation is equal to 5,000, which is the initial quantity of bacteria or the initial number of bacteria. and it decreases by 10%. So the R in this equation is 10%. 10 divided by 100 is 0.1, 10%. And then what else do we need here? We need the T, and the T is 8 hours. Okay. And we're told it decreases by 10% each hour. So we're going to have Y is equal to A is what? 5,000 multiplied by 1 minus R. R is 10%, and 10% is the same thing as 10 over 100. So, and that is 0.1. So 1 minus 0.1 raised to power decreases by 10% each hour. And we're looking for what it would be in 8 hours raised to power 8. Okay, so 1 minus 0.1 is 0.9 raised to power 8 times 5,000. Okay, and 0.9 raised to power 8 should be giving us 0.430, about that. And if you multiply this by 5,000, we should have our answer. So this is 5,000 times 0.430. Please, you can also press your own calculator and be sure I'm pressing the correct thing. Okay, so we have that the bacteria will decrease after 8 hours. So they will decrease from 5,000 to 2,150. Okay, that's it for this question. So easy. I hope you are following. The next question now will be if an investment of $1,000 grows at an annual rate of 5%, what will it be worth in 10 years? Okay, an investment of $1,500 grows. So this is an exponential growth. So we say Y is equal to A times 1 plus R raised to power T. And here, the initial amount is 1,000. 1 plus R. The rate of investment is 5%. So it will be 1 plus 0.05 raised to power what? T, 10 years. Okay. So once we're able to put all the correct numbers, I think we have done. So we say Y here is equal to, if you look for 1.05 raised to power 10 and you multiply it by 1,000, it should give you what we need. So we're going to do that. So that should be 1628.90. Okay, dollars. All right, so that's what the investment is going towards after 10 years if it grows at a consistent 5% rate. Okay, we look at the next question. In 2002, there were 1,800 rats on an island. If the population grows at 6% every year, how many rats will be there on the island in 2025? In 2025. Okay. Please pay very close attention to this question and see how we're going to go about it. It's not difficult. You just have to pay closer attention. So this question now, is it an exponential growth or a decay? This is an exponential growth since we're expecting the rates to increase by 2025. So we bring out our formula. We have a percentage here. So we could say y is equal to a multiplied by 1 plus r raised to power n. Okay. And where a is equals to 1,800 rats, which is the initial population, and the rate is equals to 6%. Then what about the time? How do we know the time? The time now will be equal to 2025 minus 2002, which is equal to how many years? 23 years, right? Okay. So if that is correct, we can then implement the formula to have y is equal to 1,800 multiplied by 1.06. I believe you know how we got 1.06, which is 6% plus 1 raised to power 23. How we got 1.06 is 1 plus 0.06. Okay? And 0.06 is the same thing as 6%, which is 6 over 100. All right. So we proceed. So you can put this into your calculator and then we'll see what we have. 1.06 raised to the power 23 times 1,800. This will give us 6,875.55. So you should know that since we are dealing with rats cannot be 0.55, so it has to be 6,876 rats. So between 2002 and 2025, the population of rats would have grown from 1,800 to 6,876 if they have a growth rate of 6%. Okay, so that is exponential growth for you. We move on. The value of a new car in 2012 was $30,000. It depreciates 4% each year. How much will the car be worth in 2026? Okay, you see depreciation. When you see the word depreciates, you should know that it's an exponential decay. So we bring in the formula for exponential decay, which is y equal to a into 1 minus r raised to power t. Okay, so what are the values we have here? We have a to be equal to 30,000 and it depreciates at 4%, r 4%. How much will the car be worth in 2026 time? So our time now will be 2026 minus 2012. So how many years is between 2026 and 2012? That is like 14 years. Am I correct? 6 minus 2 is 4. Okay, 14 years. We know that. So if this is arranged, all we need to do is to sort them into the formula, which is now y is equal to a here is $30,000. Good morning. Multiplied by 1 minus 0.04. raised to power 14. So y is equal to what? 16,940.20. So y will be equal to the value of the car in 2026 will be equal to 16,940.20. Okay, so let's see if we can take one more question that will show other aspects of exponential growth. Okay, yeah, we are here finally. Santia bought a house in 2001. The value of the house increases 3% each year. If the price of the house was 350,000 in 2024, what was its value in 2001? Did you get that? In 2024, the house was valued at 350,000. So we're looking for the initial value that it was in 2001. How much was it? Okay, so how many years between this now? 2001 to 2024, that's about 23 years. Okay, and is this a growth or a decay? It's a growth because she bought the house and it has increased. They say increases as 3%. So we have our formula to be y is equals to a multiplied by 1 plus r raised to power n. And now we have that a, where a is equal to what? We do not know the value of a, the initial amount. Don't get this mixed up. A is a value that comes before the new value. A is always the older value. Okay. In this case, a is usually the present value, and y, look at this, a is usually the present value, and y, okay, let me put it this way, the formula is y is equals to a into 1 plus r raised to power n. So this a is usually the present value, and the y is the future value that we are looking for. But in this case, since we already know the future value, which is in 2024, this is now the present value. So we are looking for the past value now. The past value. Okay. So now this is the present value. So we're looking for the past value. So this comes, a always comes before y. I hope I'm not confusing you. A always comes before y. Just try to, by the time you watch this video a second time or a third time, it will be clearer. Okay, and by the time you lay your hands on more questions, try to get practice questions and more questions. I have some questions at the end of this lecture. Try to practice as much as you can and it will help you. So back to the question. We do not know what a is now, what the past value is. So, but we know that y is equal to $315,000. And then what else do we know? We know that the rate is 3%. And this is t. Okay, t. You can use anything you want anyway. It doesn't matter. What else do we not know here? The time now it has taken will now be 23 years from here. Okay, 2024 minus 2001 is 23 years. All right. Okay, so if we know all this, The next thing is to um, lay them properly in the equation. So we have y, which is 350,000, is equal to a, which we do not know, times 1 plus r. R here is 3%, which is 0.03, raised to power what? T, which is 23. Okay, so we can straight ahead say A is equals to 350,000 divided by 1 plus 0.03 is 1.03, raised to power 23 will give you 1.9736. So if you divide this equation, the initial value will be 350,000 divided by, so it means that she bought the house for 17,730. Nope, sorry, I'm writing the wrong. It means A is equals to 177,342. That's 177,342, all in dollars. So it means that A has the value of the house when she bought it in 2001 was, so in 2001 the house was equal to 177,342, and then in 2024 the house is valued at $350,000. Okay, that's it for this question. A sample contains 400 counts of bacteria. If the bacteria doubles every 20 minutes, how many bacteria will be there in 5 hours? Please pay attention to this. A sample contains 400 counts of bacteria. If the bacteria doubles every 20 minutes, how many bacteria will be there in 5 hours? Okay, we look at this. This is exponential growth. So we say y is equal to a b raised to power t. Okay, we're using this formula, this form of the formula, because there's no rate here. So there is no percentage rate here. So what we have here is a proportion, which says the bacteria doubles every 20 minutes. So it means that the rate here is 2. It doubles, that is 2 every 20 minutes. How many would there be in 5 hours? Okay, that means if it doubles every 20 minutes, how many 20 minutes do we have in an hour? We have 1 hour is equals to 60 minutes, and it doubles every 20 minutes times 2. So it means that in 60 minutes, it will double how many times? 4 times, divided by, doubles every 20 minutes, divided 60 divided by 20 is 3 times, sorry. So what it means is that the bacteria will double 3 times in 1 hour. And they want us to know how many bacteria will be there after 5 hours. So it means that what we're going to have in 5 hours will now be 3 raised to power 5. 3 times 5, not 3 raised to power 5, times 5 hours. So what's the equation now will now be, the time is 5 hours. Okay, so if we now substitute what we have there, we'll now have that y will be equal to A is the initial count, which is 400, times B, which is the rate, 2, raised to power 3, because it doubles 3 times in an hour, times 5 hours. Okay, so 3 times 5 is 15. So in 5 hours, we're going to have 2 raised to the power 15 now will be um we'll now have 400 times 2 raised to the power 15 will be 32. Please, you can also check your calculator. If I'm making a mistake, please let me know in the comment section. 32,768 times 400. So we'll have, after 5 hours, we're going to have times 400. We're going to have this number of bacteria in just 5 hours. Okay, so 1, 2, 3. Come on here, 1, 2, 3. So we're going to have 13 million bacteria. 13,107,200 bacteria in 5 hours. If the bacteria doubles every 20 minutes, please, this is the main point here. It doubles every 20 minutes, okay? 400 bacteria doubles every 20 minutes. And in 5 hours, it will give you this 13 million 107,200 bacteria. Okay, we go on. Okay, so now we have some practice questions that I want you to try your best, lay your hands on these questions and try to do justice to them. If you have any challenges, please, you can let us know in the comment sections. Let us know how you are able to deal with all this. The first thing is to be able to differentiate between the exponential growth and exponential decay, and then you apply the formula. If it's a growth, you have to know the actual formula to apply. If you are given the equation in percentages, then you could use the 1 plus r or 1 minus r. Okay, but if you are given in terms of rates per hour, per annum, per month, then um you have to convert it appropriately. All right. Number 1, a sample contains 120 counts of bacteria. If the bacteria triples every 10 minutes, at this rate, how many bacteria will be there in an hour? This is similar to what we've just done. How long will it take for the sample to contain 2 million counts of bacteria? Okay, this now is asking us the time. How long will it take for the sample to contain 2 million counts of bacteria? How you do this, you just put in all the figures and look for the time t. Okay. Number 2, assume an exponential growth of 7% each year. If Grace bought a house for $90,000 in 2005, how much will the house be worth in 2025? Number 3, number 2 is an exponential growth. Number 3, if an investment grows at an annual rate of 2.5%, what will it be worth in 10 years? Feel free to pause the video at any time, copy the questions, and make your attempt. A bacterial culture starts with 1 million bacteria and decreases by 10% every 20 minutes. How many bacteria will be remaining after 4 hours? Question number 5. If the population of a school triples every 4 years, what will the population be after 12 years? Take the current population as 1,500. Mathematics is all about practice. Try to lay your hands on questions. Try to solve these questions here and look for more questions and keep practicing so that it becomes part of you. Okay? Let us try to see. Let us look at this practice question, the first one, so that we make sure we have done justice to everything. Okay, because this one demands us to tell the time. Okay, so let's calculate t in this question. Let me see if we have a little time. Okay, we'll be fast about this. All right, so a sample contains 120 counts of bacteria. If the bacteria triples every 10 minutes at this rate, number one, calculate how many bacteria will be there in an hour. Number two, how long will it take for the sample to contain 2 million counts of bacteria? Okay, so this is exponential growth. So we use the formula y is equals to a into b raised to power nt, where n is the number of times it multiplies itself in an hour and t is the number of hours. Okay, so y will now be equal to a in this question is 120 counts, so 120 multiplied by b. They say it triples, so b is 3. Triple means 3. How many times does it triple in an hour? It triples every 10 minutes. Every 10 minutes. And we have 60 minutes in an hour. And it triples every 10 minutes. So 60 divided by 10, that means in an hour it's going to triple 6 times. So n here is 6 times 1 hour. So we're just looking for 1 hour here. So the first question says in an hour, so it's times 1 hour. T is 1 hour. So y here, the first part of the question will now be equal to 120 3 raised to the power 6 is what? 729. So if you put all this into calculator times 729, please always confirm if I'm correct. Don't just assume I'm correct. So if everything is put into calculator, we'll be having y is equal to 87,480. So we'll have 87,480 bacteria in the sample after 1 hour. And the second question says, how long will it take, second part of the question, how long will it take for the sample to contain 2 million counts of bacteria? So now we have the formula here. Now we're looking for t. We're no longer looking for t. T is 2 million here. So if t is 2 million and we're looking for t, the number of the hours is going to take to get 2 million counts of bacteria. So this 2 million here is the future value, which is now y. So we say, I always like to write my formulas first. Y is equal to a into b raised to power nt. Remember that why we have nt is because of this. It triples 10 times. It triples every 10 minutes. That is why we have this n here to signify the number of times it triples in an hour. And remember, there are 6 10 minutes in 1 hour. So if we move this solution to this part, we can then say that if we want to substitute our figures here, we can then say y is now 2 million is equal to what? A, what's the value for A now? 120 multiplied by B is 3 raised to power what? 6. Multiply 6 times and 60. We don't know how many hours, so that's what we're looking for. So this is what it is. So what can we do here? We know that 2 million is the same thing as 20 times 10 raised to power 1, 2, 3, 4, 5. Right? So we can write this 2 million as 20 times 10 raised to the power 5. But we can still leave it as 2 million. We can write it as 20 times 10 raised to the power 1, 2, 3, 4, 5 times 10 raised to the power 5. Yeah? Is equals to 120 times 3 raised to the power 60. Okay? But in order to avoid confusing anybody, we can leave it at 2 million. So if we say 2 million is equals to 120 into 3 raised to the power 60, we can divide both sides by 120 and then see what we have left. So over 120 over 120. This to eliminate this 120 first here. So we'll be having 16,066, let's just say 667. We're going to have some approximation difference. Is equal to what is left here is now 3 raised to power 60. Now, if you remember in our logarithms, if we find the log of both sides, we're going to have log 16,667. In order to eliminate, remember we say logarithm is the inverse of indices. So we're going to have log 16,667. It's the same thing as there's a law of logarithm which says that log 3 raised to the power 60. There's a law of logarithm which allows us to bring 60 log 3. Yes, remember, if you have not seen our class on logarithm, please, you won't understand what we are doing at this point. So I'll suggest you pause the video and take a look at our class on logarithm. So you can press on your calculator now, log 16,667, and let's see what we have. So this is the same thing as log 16,667. Okay, sorry, let me just move this to this side. I'm very bad at managing space, obviously. So if we move it to this side, we're going to, if we divide both sides now by, we want to eliminate every other thing to have just t left here. So we can divide both sides by 6 log 3. And that will now give us log 16,667 all over 6 log 3. Okay? Is equals to what? T. So if you put this into your calculator, log 1667 should be giving you something like 4.222 over log 3 times 6 should be giving you 2 point, sorry, this is 4 to 4.222 all over 2.86 t is equals to this. So finally, our t will be equal to what? 4.222 divided by 2.86. 4.222 divided by 2.86. So we have that the time it would take for the sample of bacteria to contain 2 million counts will be 1.48 hours. Okay, so we can see here that in 1 hour, 1.48 hours, that's the bacterial count will move from 120 to 2 million counts. Okay. In the first part of the question, we have that in 1 hour, it will move from 120 to 87,000. And in 1.48 hours, it's going to move from 120 to 2 million counts of bacteria. That's to tell you the power of exponential growth. Okay, so in summary, in real life, we could have exponential growth in populations. We see exponential growth in populations, investment, and in certain diseases. For instance, a population can grow rapidly under an ideal condition. Exponential decay applies to radioactive materials and some financial products, demonstrating decrease over time due to constant rates. Yep. So, exponential growth. I would like to say here that exponential growth can be divided into two. Growth can be divided into two. Um, Exponential growth and logistic growth. This will be a topic for some other time as we are out of time for this lecture. So exponential growth actually is unlimited. It continues to grow higher. But logistic growth initially grows like an exponential growth and then stops to grow, stops to increase at the point of its upper limit, L1, which is called the upper limit. It continues to grow. Just for instance, like you put um um let's say, what animal can I use now? Let's say you have so many cats in an island, and okay, let's say you have 10 cats in an island and 10,000 rats. 10 cats to 10,000 rats. 10,000 rats in an island. The cats will continue to feed on the rats because the rats are so many, and they will continue to grow. The cats will continue to increase exponentially until after a time the cats will be so much that they will not have enough rats to eat, and their increase will reduce and continue to reduce. So that's what we mean by logistic growth. In our next class, I'll show you the differential equation for logistic growth and exponential growth. Okay, guys. Sorry this lecture was a bit long. I had no choice. It's so important. Thank you so much for your time. I'll see you in our next class.